I'm going to start out by working a problem. So our problem says a beam of light strikes one face of a window pane at an angle of incidence of 30 degrees. Let's start with that. We always draw a picture, so I have a window pane. We have to take a little bit of knowledge about the window pane. What can you tell me about a window pane? It's made of glass. What else? The sides are parallel. That's a really important piece of this. So here's my window pane. And then I have light coming in. What direction is the light coming from? Okay, it's coming from top down, but what angle from where? 30 degrees from the normal. It's really important that we get that from the normal. So my light is coming in. I've got to use a different angle to have any hope of getting a straight line. And just to make sure we are all of one accord, I know everybody knows the joke. They have driving accords in the Bible. That angle that I just marked is the angle of incidence. Okay, so I have the angle of incidence. What's going to happen when that ray goes into... What's going to happen when that ray goes into my my glass? It's going to refract. And which direction is it going to refract? Okay, toward the normal. Why does it go toward the normal? These are important steps along the way to understand it. Why is it going toward the normal? Because it's going into something that goes slower. Remember my example on the beach. It goes slower, so it refracts toward the normal, so it's going to come like this, and there's theta 2. Oh, you can't read that. Well, let me zoom in. Undo. There's theta 2. You can kind of read it now. Okay. I'm sorry. I'm too anal. I can't live with myself. So there's, whoops, wrong one. Shoot. There's theta 2. Now, where am I going to measure? Well, what's he going to do when it gets to the second surface? It's going to refract, but this time away from the normal. Why this time away from the normal? Whoa. Darn it. Let's pretend that was right. So now it's going to refract away from normal. Why away? Because it's going to something faster now. So now it's going to bend something like this, and there will be theta 3. Now, my picture is not accurate, but it's qualitatively correct. We do our math to get the quantitatively correct part. Now, I don't have everything from the problem. We haven't even read the whole thing. So we have the next thing, the index refraction of the glass is 1.52. What's the symbol for index refraction? N. So I'm going to have N sub G is 1.52. What about the air outside? What's the index refraction in the air outside? And it has air on both sides because it didn't go into water, right? Okay, so it travels through the glass, emerges from a parallel face on the opposite side. Ignore any reflection. So we're ignoring those 4% reflections roughly. Find the angle of refraction for the ray inside. So how do I find theta 2? Okay, so I just use Snell's law, which is the first material was air, so Na sine of theta 1 equals Ng sine of theta 2. Works for me? solving that for theta 2 is equal to, well, let me show the step in between. Solving that for sine theta 2, I have to divide both sides by ng. So I have sine of theta 2 is equal to na over ng, sine of theta 1. So now theta 2 is equal to the inverse sine. I'll put a sine today. Putting in our values, Na was 1.00, Ng was 1.52. Sine of 30 degrees. Everyone should know sine of 30 degrees, because it's 1/2. So you put that in your calculator.
19.2.
19.2 degrees.
Yeah.
Okay, so theta 2 is 19.2 degrees. So that's the answer for our first one. Then show that the ray in air on the other side is parallel to the incident light. So if I want to show that second part, what do I need to calculate? Theta 3. And what should theta 3 be if it's parallel? The same as theta 1, because it's the angle between the normal and the ray. So if I look at the light refracting here, what angle do I have to use? Well, what two angles are involved? Theta 3, and I didn't actually mark it, but based on your geometry understanding, you should recognize that this angle between vertical and my ray is the same as this angle between vertical and my ray. Hence, that's still theta 2. And so then we're going to have a problem that anyone can see their way through without putting in numbers. Because we're going to have ng sine theta 2 is the incident side, and na sine theta, and we're just going to change that 1 to a 3. Well, if all the numbers are the same except for theta 1's changed to theta 3, then that tells you theta 3 has to be the same as theta 1. So there's no point in redoing the calculation. It's all the same numbers, just reversing it. And so, I mean, if you're doing it, you would have to do your hand waving, here's why, or put the numbers in. So why did I do that? The biggest reason of everything why I did this problem was to make sure we're all clear on the angle of incidence and angle of refraction are measured from the surface normal. That was the biggest reason. And the other one was just to see using Snell's law. Now for cool things. The Mirage. How many people have seen a Mirage? Okay, that's not as big as I thought. How many people have seen Bugs Bunny seen a Mirage? Which is where I got the name Mirage, because that's how he pronounces it. When Bugs Bunny sees a mirage, what does he see? A what?
Water.
He sees water, and he sees palm trees, and he even hears music because, he's crazy from heat stroke. Well, that's not exactly what you would see. So if you've actually seen a mirage, I'll tell you, you probably have all seen a mirage, you just didn't recognize it because we had about a third of the class that said they'd seen it. When I was a child, we'd be driving down the highway in a hot summer, and I'd look up ahead and I'd be like, oh, there's water on the ground. There's water on the road. I can't wait till we get there. We're going to have to splash through the water, and it's going to be great because it won't be so hot. And I would be all excited and waiting, and we never got to the water. And pretty soon I came to realize, okay, there's no way there was water there, and it always dries up before we get there. It must not have been water. It must have been something else. But what was that something? That something occurs because the road is very hot. And because the road is hot, the air right above the road is very hot. And the index of refraction goes down. That is, the speed of light goes faster when it gets into hot air. And so you have light from the sky that's coming down to the road, but because the index of refraction is getting smaller, it's going faster, it bends away from the interface between the cooler air and the hotter air. Those interfaces are horizontal. So it's bending away from horizontal, or away from the normal to horizontal. And so it's bending more horizontal, and it ends up coming out horizontal and then going back up. And so when I look down at the road, I'm seeing light that started at the sky, came down to the road, got bent by the changing index refraction, and then came up to my eye. So when I thought I was seeing water on the road, what was I really seeing? I was really seeing the sky. But it looked like it was rippling. Why did it look like it was rippling?
Because the air's not uniform temperature.
Yeah. The air is not uniform temperature and it's not stationary. The air is moving. It's the same reason that stars twinkle. We all know the song, Twinkle, Twinkle, Little Star, right? Well, stars twinkle because you have air between you and the stars. Not all the way out, of course, only out to the end of the Earth's atmosphere. But that air has hotter and colder areas, and the air moves. As the light from the star goes through that air, it gets bent around. So telescopes actually have a limit to how precise, we call it the resolution, the smallest detail they can see because of that twinkling. So when you have a lot of that twinkling, they say it's bad seeing, and you have worse resolution. And the coolest thing of all is they have developed a way to make mirrors on telescopes that will actually deform themselves to move, to adjust for the twinkling light. And so they can actually improve the resolution by a factor of 10 by deforming the mirrors in sequence with how the light is being moved around. It's just pretty amazing. But understanding how the mirage works is really cool. And what's the best place to see a mirage? If you drive through Utah, anybody ever taken the 80 from Lincoln to Lincoln? Lincoln, California to Lincoln, Nebraska? Yeah. Well, the 80 anywhere that goes from here to California. When you're going through Utah, what do you see?
Red dirt.
Yeah. Actually, it's white dirt because it's salt flats, but you just see flat salt everywhere. And if you look north as you're driving through there, it always looks like you've got like maybe some water with a mountain going down into it because you're seeing a reflection of the mountain and the light. Or the sky. It's really, I mean, it's great. I don't think I've ever driven through Utah. Of course, I never drive through Utah in the wintertime. I always drive through the summertime. Never driven through when you didn't have really strong mirages to see there. So, understand why they work? Well, that's part of physics, and that's why I teach physics, because it's totally cool. That's not totally cool. That's not the only type of mirage. I love the way I cut out application mirage there. It's not the only type of mirage. The second type of mirage is usually seen over bodies of water. You have to have a temperature inversion. Normally, the temperature is hottest near the ground and gets colder as you go up. But if you have something like a body of water, that body of water will keep the air cooler on a hot day. And so you have cooler air down low and hotter air up above. In that case, you're going to have just the opposite. Light from the ground comes up and gets bent around and comes down. And so in that case, you can look off over the lake and see a sailboat sailing upside down in the sky. Is there really a sailboat upside down in the sky? Sure there is, right? No. What you're seeing is light from the lake coming up, refracting, and coming back down to you. And so you see that this picture is showing a house on the other side of a lake. And the house on the other side of the lake, which is inside that box, is upside down in the mirage. Well, because of the going up and coming back down. So, two different types of mirages. Next, pretty colors. I don't think this comes from Pink Floyd. In fact, I think somehow that Pink Floyd has the colors backward on their album. I'd have to go check. Or, yes, an enterprising student can check for us. When light goes through something like glass or water, it will have what we call a dispersion, a spreading out of the colors. Why are the colors spread out? Well, what makes the light, what do we call it when the light bends when it goes from air into glass? Diffraction. And what determines how much the light's going to diffract? Diffract. Diffract. The what? Well, the wavelength is where I'm getting to, but from what we've learned so far. What we've learned so far, we didn't mention wavelength. What did we talk about? What did we use in our practice problem? The what? Okay, the index of refraction, which has to do with the speed of light. So the amount it bends has to do with the difference in the speed of light. If it slows down more, it's going to bend more. If it slows down less, it's going to bend less. Well, it turns out the speed of light traveling through glass or water depends on the wavelength, as Carrie said. So different colors have different wavelengths and will diffract by different angles because they have different speeds. So when the light goes into the prism, the light that goes the fastest in the prism is going to have the smallest change in its speed and hence the smallest change in its angle. So looking at this picture, assuming it's drawn correctly, which I think I checked to make sure when I got it, which color has the fastest speed? It's not violet. Since it's not violet, we know what it is. Red light has the fastest speed because it bent the least. Because the more it slows down, the more it's going to bend. So the red light bent the least, it was going the fastest. The violet bent the most, it was going the slowest. And so the light coming out is spread out as different colors. And so we call that dispersion, and that's very useful if we want to determine what actual colors of light are present in something. So a prism is what we call dispersive because of those different speeds of light. But prisms aren't the only thing. I also said water. So I've already talked about the critical angle. The critical angle is when the transmission angle would be 9 degrees. Let's go right past that and get to water. So our first clicker question for the last 2 days, why is the sky blue? A lot of people have answers to this, but a lot of them, it turns out, their answer's wrong. And so I want to ask the question to see how people understand, and then we'll go from there. Okay, we had 7 who said reflection from water, 10 that said water in the atmosphere absorbs red. Nobody said me scattering, and 4 people said Rayleigh scattering. Okay, I will look at these individually, starting with looking at the absorption of water, of light by water. If you look at the absorption of light by water, you see that water absorbs more red than it does blue. So blue light gets through water better. And that explains things like why a glacier looks blue. Have anyone seen a glacier that's blue? It's actually really pretty. It's like bubblegum color. And it's in large part because of that. Water a collection of water also has a blue color. That is in part because of this absorption of red. It's also in part because of the second thing. And the second thing is Rayleigh scattering, which is the sole reason the sky is blue. The sky is blue because we have light coming from our sun, which is roughly white. But Rayleigh scattering is the scattering, light hitting things and bending away, bouncing off of them essentially, from gases in the atmosphere. And that Rayleigh scattering is, the strength of scattering is proportional to 1 over wavelength to the 4th power. So if you cut the wavelength in half, if you go from red light to blue light, you cut the wavelength in half, that means you're going to make the strength of the scattering 2 to the 4th time stronger, 16 times stronger. So blue light is scattered 16 times stronger than red light. So the light from the sun that comes into the Earth's atmosphere has 16 times more blue light pulled away from it than red light. So when we look at the sun, we see it with a lot of the blue light removed. If you take the white light and you remove the blue, you're left with yellow. And so the sun looks yellow to us because the blue light's been removed. But if we look at any other angle in the sky except for at the sun, light from the sun went there, and then we're seeing the light that was scattered by the atmosphere. And so what color was primarily scattered? Blue. Hence we see blue when we look away from the sun. And when we learn about polarization, we'll also learn that there is a polarization involved with that scattering. And so if you wear polarized sunglasses and go like this, look at the sky, you can make it get brighter and darker. It's totally cool. I mean, what would it not be? It's physics. Rainbows. We've all seen rainbows. We know the Bible says, I put my bow in the sky, that it should be a sign between me and thee, that I will never again send a flood to destroy man, right? One of the things that non-Christians say about we Christians is that it's basically some mythology trying to explain why things happen. And so back then, nobody knew. Of course, people who don't believe, who aren't Christians, aren't going to believe there's a worldwide flood either, but that's beside the point. That back in the Bible times, they didn't know about how a rainbow was made. And so they came up with this story that, it's basically each time you see a rainbow, it's a divine act. And now we know it's not a divine act. It's a thing of nature. Well, as a Christian, I believe what the Bible says. And so I think that, maybe God changed the nature of the atmosphere, that before the flood, you didn't have the water droplets in the air necessary to make a rainbow or something, so that you could have a rainbow after the flood, but not before. But let's look at the physics, how we understand a rainbow to be made. A rainbow is made when light hits water droplets in the atmosphere. The light from the sun, basically white, hits the water droplet, and you have the violet light refracted more than the red light for the same reason the prism. The red light goes faster through the water than the violet light. So you have more refraction of the slower speed. Then it comes and hits the backside, and at the backside, so at the backside here, you have total internal reflection. How do you get total internal reflection? Yeah, you hit less than the critical angle. So it's coming farther from the normal than the critical angle. Now, do you always have, I'm pretty sure for the rainbow here, you have total internal reflection. I didn't check that before just to make sure. So you have a reflection, and notice that the violet light came down here below the red, but then after the reflection, because of the difference in angles, the violet light crosses over, so it's above the red. So you have one crossing between the red and the violet. I'll redraw the red as well, just so we can. Yeah, nice job. So we have one crossing, and then it comes out, it refracts again, and so the red light, like that, the violet light, like this. Now, if you look at those, it's kind of hard to tell here. They look pretty close to parallel, but they're not parallel. Which one is closer to horizontal?
What?
It is exaggerated here so we can see better. Which one's closer to horizontal, the red or the violet? Okay, the violet is closer to horizontal. Now, if we're standing on Earth and we have these droplets that are doing this, the first thing to note is this is backscattered. The sun comes from the same side that the light goes toward. And so if you're looking at a rainbow, you have to have the sun behind you. So if you see a rainbow up here on the screen, where's the sun? Back there. Now the second thing is these angles are pretty much exact. They're set by geometry. And so the angle, and I think I have it on the next slide, is something like 42 degrees. Yeah, 42 degrees from the sunlight to the red light and 40 degrees from the sunlight to the violet light. So if I look up in the sky, I'm going to, as I start the horizon and move up, the first color I'm going to come to is the one that's the closest to horizontal. What color is that going to be? Violet. So as I look from the ground up, I'm going to see violet first. And as I keep going, I'm going to go through the rest of the colors until I get to red last. Now I said up, but those angles are fixed. So that means if the sun's over there, it's always going to be 40 degrees from the sun to where I see the violet. So the sun goes here, I just look through my head and say, okay, 4 degrees from there, there's the violet making a circle. And if I go up to 42 degrees from there, I'm going to have the red making its circle. And so how can I determine the sun's exact location if I look at a rainbow? Yes, but to determine its exact location, it's actually easy. Find the center of that rainbow, right, because that's where the zero is. From there, through your eye, and keep going back, the sun's on that line. So the sun is directly on the line going from the center of the rainbow through your eye, and then back behind you. So rainbows are made, that's what we call the first order rainbow. First order, because it's the first one, the lowest one you see. Now, if you look in this picture, something that's cool to notice, do you see a difference between the light here and the light here? What's different? Starker. This region here is actually called Alexander's dark band, not to be confused with his ragtime band. It's called Alexander's dark band because the dude, last name of Alexander, noticed it. What's going on here is, well, notice you can see the background very clearly in the dark band. That means you're not having light scattered toward you from the clouds. The water droplets aren't scattering toward you. Whereas over here, you have a lot of just white light obscuring the background because you have a lot of light scattered toward you inside of the rainbow. Then you get to the second order bow. The second order bow is shown here in this picture. Light again comes and hits the water droplet. It refracts, and now it reflects. Okay, didn't want that color, want this color. It reflects 2 times. And because it reflected 2 times, you have a reversal from each reflection, so the color and the angles reverse again. So it turns out that now the one that's most horizontal is going to be red, and the one that's most vertical is going to be violet. So if you look up further, and you notice these angles, the angle between the incident and reflected is bigger angles than the 40 and 42. So you look up higher in the rainbow, and you're going to see the second reversed rainbow. So here we see the first order bow, Alexander's dark band. And here is the second order bow. And it's really hard to see the colors in here, but I can see a yellow here, yellow there, blue there, blue there. The colors are reversed. So the second order bow has the colors reversed. It has them be reversed because of the 2 reflections. So here's the actual geometry for the first order bow and the second order bow. The first order bow is between 40 and 42 degrees. The second order bow is between 52 and 54.5 degrees. Yeah.
What's the reason why the second one was
The reason it's lighter is because you're going to have more light lost because of these. At each reflection, you are losing some light, and you're going to have 2 reflections, more light lost. And I believe in theory you can make higher order bows, but I've heard people talk about 3rd, 4th, and 5th order bows, but I've never actually seen anything to indicate, yeah, we really saw it. Just like, I did, trust me, it was there. So, now I know, like my first year of teaching, I didn't go over the 2nd order bow. And then my students took the MCAT, and the MCAT had a question about the 2nd order bow. So I want to make sure that I cover both the 1st and 2nd order bows. And you understand the 1st order bow is a single reflection off the back. The colors are spread out because of the different speeds of light in the water droplet. 2nd order bow, 2 reflections in the droplet. Question?
Is there another Alexander's dark band on the other side of the 2nd?
No. The reason you have that dark band is because you have light that's scattered in between, but it's scattered forward rather than scattered back. And so you don't see it. So that's why it's dark, because it's being scattered forward instead of back. It is pretty dark out there beyond it, but you're not having much action. There's not another dark band beyond. Okay, so clicker question. What color is on the inside of the 1st order rainbow? And we got the picture there to help us remember how that came out. Okay, everybody's answered. We have a very strong agreement. Very surprising. The correct answer is the violet or blue. I'm not sure how anyone said yellow or white. Let's just go back and look at a rainbow, because
Depending on how you frame inside, I didn't answer it, but in defense of whoever did, it's on the inside of the rainbow.
in the center between the inside and the outside. And where's white in the rainbow?
It's the white lights on the other side of Alexander's.
Okay, maybe that's what somebody meant, because there's no white in the rainbow, but maybe they meant the place where you have that white backscatter. I hope so. It's a waste to come to class and not learn anything. All right. Now we're going to talk about images. An image is what you see when you look at something. An object is the thing you're looking at. So, for instance, when I look at Jerry, what I'm seeing is technically an image. And I can perceive a position for that image. And, of course, that position for the image should be where Jerry is, right? Because it's very direct. But if I had a mirror between me and Jerry, and I didn't know that there was a mirror there, the mirror might be set up here, and I look and I say, hey, look, there's Jerry over there. But in fact, Jerry's over here, and I have the wrong location because of the mirror. And if you've played, video games in the arcade, when you're playing that video game in the arcade, do you know where the screen is that you're looking at? Yeah, it's down here. But you look and you think you're looking at something out here because they're using a mirror and you're seeing an image of the object. The object's down here, but the image is over there. So we're going to look at image formation. Now, image formation has everything to do with the rays of light. So if I look at something, so in this picture here, we have a bottle. Light from the top of the bottle goes in all directions. There's only 2 directions shown in this picture. Why only 2 directions shown in this picture? Anyone? Bueller? Nobody has any idea why it shows only 2 lines coming from the tip? It's because my eye allows a certain range of light in. My pupil is not a single point. The pupil is what we call the hole in the eye that lets light through. The pupil is not a single point. It has a certain area. And so light can come at different angles from that tip and make it through my eye, but it's only showing the range of angles that will make it into my eye coming from the tip. So the other rays of light, the light going like, let's say, this direction or this direction or this direction, that doesn't reflect off the mirror and make it into my eye, so they didn't show those. They just didn't want to confuse. But do remember that light's coming from that tip in all directions. So the light from the tip that goes into my eyes, as the light goes away from the tip, it travels as a ray. So it's traveling in straight paths. Different angles means it's going to start separating. Gets to my eye, and my brain says, look, I had light that was coming like this, extrapolate back, and it met this far away. And so my brain says, those rays met back here. Now, if I know there's a mirror there and I understand mirrors, I can figure out, that's not where it was. But I'm sure you've seen videos of like animals seeing a mirror for the first time. They get very confused because they don't know what that's doing, but they know what their brain is telling them about where the object is that made that image. And so where those rays extrapolate to coming together, that's where our brain says the image is. So the image location is here. The object location is here. And then we're going to use geometry to figure out how the image and object positions relate. So if you look at this, now it's pretty obvious because the mirror has the same angle of incidence as angle of reflection. I can take this ray and just reflect it back, and this dashed line is a reflection of the incident ray coming back. Incident means coming from the object to the mirror. And so just based on geometry, these triangles should be identical triangles because I have the same angle coming down both sides, the same vertical distance, the same angle. Yeah. They're identical triangles, which means that the object distance and the image distance are the same. So for a plane mirror, distance object equals distance image, except for one important fact. What's that fact? If the image is on the other side of the mirror from the object, then it's a negative image distance. If it's on the same side of the mirror, it's a positive image distance. So that negative sign means it's behind the mirror. So the distance object is positive because it's in front of the mirror. The distance image is negative because it's behind the mirror. So that's how images are formed with a plane mirror. It's kind of boring, right? But we can do things to make it more exciting. Here's some sign conventions to keep in mind as we work with optics. Number one is, this doesn't come from your textbook. It comes from a different textbook because of the chapter number, I can tell. You have different conventions for what you're going to use for symbols. P, often used DO, often used S, is the object distance. OBJEC. So it depends on what book you're looking at or what website you're looking at, what symbol it's going to use for the object distance. So I've got 3 options here for you. And so the object distance should always be positive. It says here if it's a real object. A real object means that the light rays are really there. So if your object is a physical thing, like your object is Jerry's Beats headphones, it's a physical thing. The light rays are really here coming from it. Hence, it would be a positive object distance. For the image is a real image if the rays really meet at the image. Did the rays really meet right here at the image? No. That means it's not real. It's virtual then. If I have a projector here, are the rays really meeting on the screen? Yes, they are. The rays are really meeting on the screen, so this is a real image. Now, you haven't done the optic stuff yet to understand why they're really meeting, but here's a key that helps you differentiate. If you put something here and you can see the image on that, like you put a screen or piece of paper and you can see the image on that paper or screen, then it's real. The rays are really there to make the image. If you put a piece of paper there and there's nothing, then it's virtual. The rays didn't really meet there to make the image. So here the rays did not really meet there to make the image. It was just our brain's extrapolation. Here the rays really meet to make the image on the screen that it forms the object for you viewing it. The image distance, it shows Q there. Other common things, D sub I or S prime equals the image distance. And you have the same rules for image distance as you have for object distance. If the rays really meet, then it's going to be positive. If the rays don't really meet, then it's negative. If it's positive, it's real. If it's negative, it's virtual. Then we have things we haven't talked about yet, focal length and magnification. At the end of last class period, I showed you the focal length for a lens. That focal length was the distance from the lens to where the rays all met. That would be our image position we now can understand if I had parallel light coming in. And if I have a converging lens or mirror, it's going to have a positive focal length. So if parallel rays come together and meet, it's a positive focal length. If they spread apart, if they diverge and don't meet, then it's going to be negative. Now I'm going to show you some diagrams. Actually, I'm going to do it for real here so we can understand it. So let me just do that now. So here I have the parallel rays.
Are you able to turn off the monitor?
That monitor? This one?
Yeah.
Okay, so I have those, and I'm going to put two different types of lenses. First, this lens here, is that converging or diverging? Converging because it comes together. So the converging lens, you may have a hard time seeing this, but this is convex on both sides. Convex means it's bowed outward. So if it's thicker in the center, thinner on the edges, it's converging. We talked about last class period why, because the light bends, because it's slower in the glass. When it goes in, it bends toward the normal. When it leaves, it bends away from the normal. This is curved on both sides with a convex shape. So on both surfaces, it's bending inward. You can see that my image is not perfect. You have the first crossings back here, most of the crossings around here, some crossings all the way out here. That's because this shape is not perfect. If it was perfect, well, you want to have the same amount of bending on both surfaces. In this case, it would be best if it was shaped like flat on one side and curved on the other. This here would give me the best focus. And you can see, indeed, that was a better focus because it's doing about the same amount of curving on both the front surface and the back surface. So when you're making an optic system, that's something that you keep in mind if you're trying to make a precise one. Where did I just put the other? I set it down here. Here is a lens that's thinner on the center, thicker at the end, or top and bottom. And here we see the light diverges, it bends away. Does it come to a focus? No. Does it have a focal length? Yes. How can it not come to a focus and have a focal length is a really good question. Well, what you do is you mark where the light goes coming out. And you say, now if my eyeball was back here, so here's my eyeball, I would see it as if all of these rays came from a point somewhere back here. And so then I would take a meter stick, straight edge, and, wow, that was a good line, draw the continuations of these lines. And the place they meet here is the focal point. But that focal point for a lens, if the image is on the same side as the object for a lens, it's negative. That's just the opposite from what it was for a mirror. And you might be frustrated. Wait, they're opposites. The way I think about it is you have a right position and a wrong position for the image. If I have a mirror, the light should reflect back, so the image should be on the same side as the object. So that's positive lengths if the image is on the side the light goes onto. For a lens, the light should go through. So it's going to be positive image distance if it's on the opposite side because the light should go through. So here for a lens, it's on the wrong side, so it's a negative focal length. We measure the focal length. Actually, I have my symbols reversed. We use capital F to mark the spot and lowercase f to indicate the distance. So the focal length is the distance from the center of our lens to where the light actually came to a focus. So that's a negative focal length there. This here, a positive focal length, going from here to the center. Now I said to the center, this is an introductory class. Because it's an introductory class, we are going to always assume that our lenses have no thickness. Now clearly this lens has a thickness at its minimum that's about 1 centimeter. But still we're going to make the assumption that it has no thickness. So we use the center as the point where the mirror, or lens, exists. Now this was looking at lenses. What kind of lens diverge, spread out the light? What kind of lens was that? It's concave because it's thinner at the center, thicker at the edges. So if it's concave, thinner at the center, thicker at the edges, it's going to diverge the light and have a negative focal length. Put this lens out here, it was able to take that diverging light and make it come to a focus. How do you suppose the distance from the lens to the image is where it comes to a focus, is going to change if I take out the diverging lens? Well, okay, three options. I didn't hear what you said, so sorry, stop it. It will be closer. Okay, I had somebody said it's going to be closer to the lens. Is that what you said? Or
Yeah, I said the distance would decrease.
Okay, the distance will decrease. Why did you come to that conclusion?
Because the light won't be spread out.
Yeah, it was spreading here, and then it had to bring it together. If it's not spreading, it doesn't have as much change to bring to the same place, but it's going to change the same amount. So, indeed, it moved closer. Now let's change to a mirror. So here's a mirror that is concave. It's bent in. Put it here, and change it so the magnet's on the right side. It's like, why is it not sticking? What does that mirror do if it's a concave mirror? It reflects it, and does it come to a focus? Yes. So is that a positive or a negative focal length? Positive because it's on the correct side. It's on the side that the rays go. So that was a concave, now a convex mirror. What's it doing there? It spreads it out, diverges the light. So a convex mirror is diverging, whereas a convex lens is converging. They're doing the opposite things. Why does a mirror do this? Because the angle of incidence is equal to the angle of reflection, but with the curving surface, the angle of incidence is changing with where you hit the mirror. So we can focus light with both a mirror and the lens. It turns out my time is up, so I'm going to stop here.